All right, good good morning, Stat 512. Um, yeah, good morning, plus or minus 12 hours. So we just finished last week's discussion. What did we talk about? We talked about bivariate relationships, right? We talked about the idea of when you want to explore a potential possible relationship between two quantitative variables. The first thing that you should do is start with a scatter plot, right? Scatter plot gives us insight into the form, direction, and strength of any possible relationships. If we observe a linear relationship, we could specifically quantify the direction and strength of that relationship with something called the correlation coefficient, right? So a correlation coefficient close to 1 indicates a strong positive linear relationship. A correlation coefficient close to -1 indicates a strong negative linear relationship, which begs the question, well, what's this linear relationship, right? What is the line that we think best describes this relationship? We said that's the goal of regression modeling, at least in the context of what we call simple linear regression, which is just one x and one y. Right, so we talked about how we could use SAS to come up with best estimates for the y-intercept and slope to sort of what we call fit this line. We talked about we can use this line in a few different ways. We said sometimes interpreting the slope provides insight into whatever it is that we're trying to study. We also said that you could use it to generate predictions. Finally, we concluded with a discussion of the four-finger assumptions associated with regression modeling, right? You need to know what those are. Learn them and love them, right? Assumption 1, the mean is 0. Assumption 2, homoscedasticity, right? The variance doesn't depend on x. We have a common variance. Assumption 3, the errors follow a normal distribution. Assumption 4, right, the 4th of July assumption, the independence assumption, that the errors are independent of one another. So we're going to continue working our way through Chapter 5. We'll eventually finish it this week. And then we'll see that Chapter 6 is actually quite short. So we'll also do Chapter 6 this week as well. All right, so let's go ahead and work with our beloved bear data set. It's a data set that actually we're going to use quite a bit in this class. It's got a decent size, right? Close to 100 observations. I think 99 exactly, right? I got anytime you forget the size of the data set, right? You just think I got 99 problems, but a bear ain't one, right? So that's something to be grateful for in this season of gratitude. And it's got a number of variables to work with. I think we've had some exposure to it in Stat 511. I believe it's also used in some of the review exercises that I put together. As you may or may not recall, the actual goal, I mean, it's a real life data set, right, of 99 bears, and they were gathered and different attributes of the bears were measured. The goal was basically to find variables related to a bear's weight. So the y variable in this case for the researchers that gathered this data was weight. And they wanted to find like what are some variables that could be used to help predict a bear's weight. I don't know, maybe kind of like the horse example we talked about last week, right? Maybe we want to give them some sort of medicine, and right, the dosage is going to be dependent on what their weight is. And so there's a lot of variables in there. I just picked one somewhat at random, and that is the bear's neck girth, right? The girthiness of that bear's neck, which is I think the circumference, right? The circumference of their neck, right? As if imagine you're fitting that bear for a necktie for a nice little bear black tie affair, and you know, you'd measure that neck, wrap a little ruler around it, and that's our x variable. So what do, right? We have our two variables, right? This is kind of just review. This is our limbering up exercise, right? We're doing some stretches before we get into the week's heavy lifting. So We can always start with a plot. We saw proc G-plot last week and the plot statement. And so that's our scatter plot. What are your thoughts? What are your thoughts when you look at that scatter plot? Yeah, I agree. It does look like a positive linear-ish relationship, right? As a bear's neck girth increases, it appears that the weight of that bear also tends to increase, right? Girthier necked bears tend to be associated with weightier, heavier bears. There's a couple other things that might be worth observing, even though we're going to have to kind of table a more in-depth discussion about these observations. One, you may or may not agree with me, but when I look at that scatter plot, I think that I maybe see like a little bit of curvature. That is, a line probably would fit it pretty well, but I do wonder if a curve might fit it even better. Right? That is, towards the end, it actually looks like the kind of that linear relationship might be steepening a little bit. Now, as of now, we don't have the tools to kind of address something like that. So as of now, the best we could do is fit a line. But we will revisit this exact scatter plot and explore the question on whether or not there is some sort of curvature and whether or not that might in some way build a better statistical model by taking that curvature into account. The second observation that we might make is that it looks like this line gets more spread out, right, as we move towards larger and larger values of x. Does that make sense to you? Or at least, I guess, do you see that? This is called like a funneling out pattern, right? If you think of that line, the points are very tightly packed about that line initially, but as we move along that line, the points start to kind of spread out and spread out and spread out in this kind of funnel shape. Now, in terms of revisiting those assumptions from last week, something like this, when I observe a funneling pattern like this tells me that that assumption 2 might be violated. Right? Assumption 2 is the variation about our regression line. And the homoscedasticity assumption says that variation is the same. But that doesn't appear to be what we're seeing, right? That is, we're basically seeing for small values of x, the points are very close to the line, i.e. very little variability. But as we move along that line, we see the points getting spread out more and more and more. That's indicative of larger variation. So looking at this makes me think that larger values of x have larger variation associated with their error. The error is just how far those points are above or below the line. And so that makes me wonder that maybe the second assumption might be violated. Again, nothing we can do about it now. We don't have the tools. It's going to take us time to get there. But I think it's worth kind of giving you an example, something a little bit more kind of applied to the sort of theoretical assumptions that we talked about last week. So we see something. Right, we have a little bit of question marks, but a line does seem to fit it pretty well. So what would our next step be? Exactly. Our next step would be to calculate a correlation coefficient. Although before we do that, let's take a look at proc SG-plot. A newer proc, part of some of the newer versions of SAS. It's, I believe, in your little SAS book if you want to look at some of the other bells and whistles associated with it. Here the syntax is a little bit different. We use a reg statement, and that's going to fit a regression line to our scatter plot. And so it is, right? This is using the nicer um, ODS output. There's all our points. We can kind of see that line. It does seem to go through them pretty well, although again, I still think I see maybe a little bit of curvature there. But the line does seem to fit it pretty well. So I'm going to expect, let's think about the type of correlation. We're going to do correlation in just a second. What is the value that you're expecting? Again, right, pop quiz. Do you expect it to be negative 0.9, negative 0.1, 0, positive 0.1, or positive 0.9? Exactly. Of all those options, I would expect it to be closer to positive 0.9. If you're not sure why, you should definitely email me and or come to my office hours and or visit our graduate assistants. So how strong is this linear relationship? We could answer that question with proc core. Again, we're familiar with that syntax from last week. And there it is, right? In fact, it's stronger than 0.9. It looks like that correlation with a little bit of rounding is about 0.95. So a very strong positive linear relationship. A line does seem to fit it quite well. Although again, it doesn't mean that a curve might not still fit it better. Yeah, so there we are. Very strong positive linear relationship between a bear's weight and its neck girth. So the next natural step from there is what? Okay, there's a linear relationship, a strong linear relationship. What is that linear relationship, right? What is the line that describes this linear relationship? And we can find that out with proc reg. So there's our syntax for proc reg. The model statement. You're going to be using the model statement a lot, not just in this class, but really all of your modeling classes from this point on. Y variable on the left, X variable on the right, connect it with an equal sign. There's our proc reg output. At this point, a lot of it's gobbledygook, but the two numbers that we do know from last week are the parameter estimates. Our y-intercept is negative 243, point blah, blah, blah. Our slope for the x variable, the x variable is a neck girth. The slope for neck girth is 20.53122. So we could put that together and build our least squares regression line, our prediction equation. That should be reasonably straightforward to go from the previous slide to this one. In the next couple slides, I'm going to interpret these things. So, I mean, if you want to right now, you can write down your own interpretations, right? Pause the video, write down, okay, how do I interpret that y-intercept? How do I interpret that slope? And then, of course, unpause it and compare with my answers. I'm getting ready to transition slide right now. So our slope was 20.53. For every 1 centimeter increase in the girth of a bear's neck, we expect to see its weight increase by 20.53 pounds, right? For every 1 unit increase in X, the slope is the amount of change we expect to see in Y. The y-intercept, beta naught hat, is negative 243.17. That says that if a bear has a neck girth of 0 centimeters, that's a scrawny pencil-necked bear, then we expect its weight to be negative 243.17 pounds, right? Which makes us say, like, what the cutta? How can a bear have negative weight? Did it get sucked into some sort of black hole into a negative dimension? Well, no, not really. It just doesn't make sense for a bear to have a neck girth of 0. And so, not surprisingly, the y value associated with that is also nonsensical. Easy enough, right? That's our nice review. If you feel good about that example we just walked through, then you're in good shape. You could take week 1, you could cross it off. You've mastered that one. And so let's move on to mastering our second week. Recall from last week that beta naught hat and beta 1 hat are best guesses for the unknown parameters beta naught and beta 1. So a natural inferential question is, what sort of plausible values for beta naught and beta 1 are implied by beta naught hat and beta 1 hat? Right? And we know from our review exercises that questions of statistical inference can be answered in one of two ways. They could be answered with confidence intervals, or alternatively, they could be answered with hypothesis tests. In this context, we typically, statisticians, researchers, typically explore this particular question through hypothesis testing. In particular, this is typically the hypothesis of interest. A hypothesis test for slope. And again, I'm assuming that you're comfortable with the basics of hypothesis testing. What's a null hypothesis? What's an alternative hypothesis? What's a p-value? What's a significance level? What's an alpha? What's a type 1 error? What's a type 2 error? I am assuming that you know all of that. And if you don't know that, you need to go to the review material, you need to talk to me, you need to talk to our graduate assistants. There's a pretty strong support system that we have built over the years, but you need to be proactive and take advantage of it. So, our typical hypothesis test is that beta 1, the slope is 0. That's our null hypothesis, our H0. Our H1, our HA, our alternative hypothesis is that beta 1, the slope is something other than 0, right? Beta 1 is not equal to 0. Okay? Beta 1 equal to 0 versus beta 1 not equal to 0. Does that actually make sense? Like, of all the things that we could test, why 0? Why do we care whether the slope is 0 or something other than 0? Exactly, right? Because that's really basically testing whether or not there is a relationship with x, right? Because if the slope is 0, then our equation now has 0 times x. The 0 kills the x. It removes the x from our equation, right? So the slope being 0 basically says x isn't in our equation, which is basically, right, saying that there's no relationship between x and y. If the slope is anything other than 0, then the x is preserved, the x is in our equation, and so there is some relationship between x and y, right? So wait, we're going to specify this in words in the next couple slides, but we're really testing, right, null hypothesis, there is no relationship, no linear relationship between x and y, and the alternative is that there is some linear relationship between x and y. Yeah. So, right, remember when we do a hypothesis test, we're going to make one of two decisions. We're going to reject the null hypothesis. That's one possibility. That's a kind of roundabout way of saying that we like the alternative. Or we could fail to reject the null hypothesis, which is an even more roundabout way of saying that you like the null hypothesis. So if we reject the null hypothesis, that basically means that we think that x gives significant information in the prediction of y. Our linear model is better than no model at all. Although we should always keep in mind, just like we saw with the scatter plot, that doesn't mean that there may not be a better, presumably more complex model, right? Maybe some curvature, for example, would fit that neck girth data set or that neck girth weight relationship better. If we fail to reject the null hypothesis, it could and often does mean that X provides little help in predicting Y. Although it could also mean that the relationship in question is nonlinear, right? If we're working in the context of simple linear regression, that second bullet point could be confirmed by looking at the scatter plot, right? This is sort of analogous to the example we did last week. Remember where we looked at the relationship between time spent studying and grade on a test? And we drew that kind of like that quadratic curve that looked like a frowny face. And we said in that situation, if we tried to fit a correlation, the correlation would be 0. Similarly, if we tried to fit a slope, the slope would look like 0. And we would fail to reject the null hypothesis. So we want to be careful, just like with correlation, we want to be careful saying there's no relationship. It could be that there's this sort of quadratic relationship. Some part of it goes up, some part of it goes down, and they sort of cancel each other out and make it so that if we try to naively fit a straight line, it ends up being flat and looking like no linear relationship. So those are our null and alternative hypotheses, right? I think in the review notes, I sort of talk about what? In the review notes, I talk about a 4-step process to hypothesis testing, right? Do you remember the 4 steps? Exactly, right? It's like this beautiful ballroom dance, right? Step 1, step 2, step 3, step 4. Step 1, step 2, step 3, step 4. Step 1, set up our hypotheses. Step 2, create a test statistic. Step 3, use that test statistic to generate a p-value. Step 4, compare that p-value to your alpha, to your significance level, to make a decision, right? Set up the hypotheses, construct a test statistic, where's my p-value, make a decision. So we talked about step 1, here's step 2. The test statistic looks like this. This is actually a very, very familiar sort of general formula for constructing a test statistic, right? We're doing a hypothesis test for beta 1. We want to see whether or not it's equal to 0. So what do? We take our best guess for beta 1, which is beta 1 hat, and we look at how far that is from 0, right? I mean, that should be very intuitive to us, right? Beta 1 hat minus 0. Remember, 0 is a distance operator. Beta 1 hat minus 0 is basically saying how far is beta 1 hat from 0? I think the slope might be 0, so I calculate a good guess for the slope. And I look at how close my good guess is to 0, right? If it's very close to 0, then I probably think the null hypothesis is reasonable. If it's very far from 0, I probably think my null hypothesis is not reasonable. Now, as statisticians, we never deal, right? So our slopes are in our original units. So depending on the problem we're working with, right, that numerator is in units of, inches or dollars or pounds. Statisticians don't deal in those units. Statisticians, researchers, deal in units of standard deviations. So we take that distance, we divide it by the standard error of beta 1 hat. Remember, beta 1 hat is a statistic. A statistic, I don't know that we emphasized this part last week, but a statistic is a random variable. All random variables have, most random variables have means, standard deviations, probability distributions. So what we're basically doing, the standard error just means the standard deviation of a random variable. In this case, beta 1 hat. So beta 1 hat minus 0 divided by its standard deviation. It's just like the Z formula, right, that you used in your basic statistics class. Right? Most hypothesis tests, a lot of hypothesis tests look like this. I want to test whether something is equal to 0. I get my best guess. I subtract 0. I divide by the standard deviation of my best guess. You'll see this type of formula a lot. Now, right, our program is very hands-on, very real world, very application driven, which, right, I think is fantastic, especially for getting you a job and making you some money. Everyone loves money. But it does mean that we occasionally have to hand wave some of the mathematics. So here's where I hand wave the mathematics. We could prove mathematically, and you actually might do this in Stat 506. One of the classes I haven't taught in our program, but I believe you might prove at some point some version of this. Regardless, for now you could hopefully take my word for it. We could show mathematically that this thing follows a t-distribution, right? So again, a t-distribution is something that I went over in our review lecture, our review material. A t-distribution is something that looks a lot like a z-distribution, right? The t-distribution is centered at 0. It looks like a bell curve. It actually, to the human eye, is pretty indistinguishable from a z-distribution, right? A z-distribution is a normal distribution with a mean of 0 and a standard deviation of 1. T-distribution also looks like a bell curve centered at 0, except it has what's called fatter tails. It has more area, more probability out in the tails than the z-distribution does. Also remember that every t-distribution has associated with it degrees of freedom. You can almost think of the degrees of freedom as kind of like its standard deviation. The degrees of freedom, it's a technical term, I know, but it's just like a number that controls like the shape of that thing, right? Different degrees of freedom look slightly different. Again, a human eye probably couldn't perceive the difference between, say, a t-distribution that has 30 degrees of freedom and a t-distribution that has 40 degrees of freedom, but there is a difference there, right? If you measured the area underneath the curve, they would be a little bit different. The shape, the general shape stays the same, but the tails kind of change a little bit, and the changing of the tails kind of shifts around the probability underneath the curve. Right, so we have a t-distribution. Its degrees of freedom are the sample size, that's n, minus 2, right? Why 2? I mean, the real answer to that question is kind of technical, but like a somewhat accessible answer is that we're estimating two parameters, right? We're estimating a y-intercept and we're estimating a slope. And so we take our sample size and we subtract 2 for those two parameters that we're estimating. All right, so remember we had 99 problems, but a bear wasn't one. Our sample size was 99. 99 minus 2 gives us 97. So we have a test statistic. It follows a t-distribution with 97 degrees of freedom, and that test statistic, we can get it from our output. I'm going to show us in just a second. We could get it from our output, and it's 28.58. All right. So let's go to the parameter estimate section of the output. Let's look at that neckline. The neck, remember, is the parameter estimate for slope. And look where it says t-value. T-value is 28.58. Now, incidentally, just take that parameter estimate, 20.53122, and just real quick in your head, divide it by 0.71843. We'll see who does it first. Go. Ha, that was fast. Exactly, 28.58, right? So the standard error, remember the test statistic is 20.53 minus 0. So, I mean, it doesn't really do anything. So we really are just doing 20.53 divided by 0.718. Put that in your calculator, you'll see you get 28.58. That's our test statistic. Now notice, right, where the line says degree of freedom 1, it's doing something a little bit different there, and we'll talk about that next week. But if we're talking about the T statistic, its degrees of freedom are 97, not 1. Okay? So for now, kind of ignore that degree of freedom column. It's kind of like a red herring. It's like it's there for a reason, but it's communicating kind of the wrong information based on kind of what we know at the moment. So trust me, the degrees of freedom for our test statistic are in fact 97, despite the fact that it looks like SAS is trying to claim that it's 1. So that's step 2, right? Step 2 is 28.58. Now, step 3 is what? Step 3 is where's my p-value? Incidentally, the p-value is right next to the test statistic. So here the p-value is very, 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 very small, indicating that there's strong evidence that we should reject the null hypothesis, right? Anytime your p-value is less than alpha, and usually we're going to use an alpha significance level of 0.05, of 5%. Usually when your p-value is less than 0.05, we reject the null hypothesis. Here, it's a lot less than 0.05, and so we have strong evidence that we should be rejecting the null hypothesis. So that p-value less than 0.0001. Okay. Let's think about how we would get that p-value using a table. Okay. So here's the t-table from our textbook. The rows correspond to degrees of freedom. So that's our t distribution. We can see it looks like a bell shape. You see the picture of it up in the top right. So it looks like a bell-shaped distribution. It's got a mean of 0, symmetric. And then it's got some cutoff point. It's a little hard to see, but it's shading all the area to the left of that cutoff point. So it's giving us what's called the cumulative distribution function for a given value. For some given value t, it's giving all the area to the left of that. Okay. So to find our p-value, the first thing that we need to do is find the appropriate degrees of freedom, right? We have 97 degrees of freedom. So if you look at those rows, it goes like 1, 2, 3, 4, 5, and then right goes to 10 and 15. We go all the way down to 30, and then it starts actually skipping, right? Because a paper can only be so big. So it goes 35 and 40, 45, 50. Unfortunately, 97 is not on our table. So the convention is anytime that it's not on the table to go down to the lowest degree of freedom, right? I wouldn't call it rounding, because even if our degrees of freedom were 99, we would go down to 90, not up to 100. So the rule of thumb is to go down. It gives us what's referred to as a conservative estimate. It's going to make the p-value larger than it really should be, right? Going down makes the p-value larger than it should be. Going up makes it smaller than it should be. And so sort of the consensus in the statistical community is that we would rather say the p-value is too large than to say it's too small if we have to err one of those two ways. All right. And so basically, right, what we do is, so we find our row, it's going to be the 90, so we have 90 degrees of freedom, and we start going across that row. So we have 0.126, 0.387, 0.677, 1.042, 1.291. We can keep going and going and going. And we're basically looking to try to find the number that's closest to our test statistic. Our test statistic is at 28.58. Now, in this case, notice our 28.58 is sort of like off the chart. It's like way off the chart. right? Because our chart only goes as far as 3.4. 3.4, I go up, it looks like it's in the 99.95 column. So that's like, what is that? It's like 0.05%. Right? So what that's saying is that value, 3.402, if we're talking about a t distribution with 90 degrees of freedom, there's only 0.05% of the area to the right of that 3.402. And then 28 is like way over there, so there's even less area to the right of 28.58. Right? So based on this, we could say that our p-value is less than 0.0005. I think if I'm converting my it's awkward that it's written as a percent, not a decimal. Yeah, I think 0.0005 is correct, right? So the area to the left of 3.4 is 0.9995. It means the area to the right, which would be the p-value, is 0.0005. And we actually know it's smaller than 0.0005, but we don't know how much smaller because, right, our table's somewhat incomplete. All right, so I say it's less than 0.0005, but that's not exactly right because the p-value is not the area to the right of our test statistic. Well, it's not just that, right? Because this is a two-sided test. And so we know from the review material, the p-value is actually 2 times that area. We got to take into account the area to the right and the area to the left, right? The p-value is basically the probability of a t-distribution being greater than 28.58 and the probability of a t-distribution being less than negative 28.58. Okay, so we actually take that 0.0005, we double it, which would be, I guess, 0.001, and say it's less than 0.001. Although SAS gives us a more precise estimate we saw by saying it's less than 0.0001. Okay. I know that I'm not going into like a lot of detail on this because again, like a comfort with t distributions should be part of like a basic general education statistics class. So, right, again, for better or for worse, I'm sort of taking it for granted that you kind of actually knew what I'm talking about right now before this class even started. And I know that's true for some of you, but I also know it's not true for some of you as well. And of course, I can't know who's who. So if this isn't making sense, you got to hit that review material. And if it still doesn't make sense after the review material, you got to reach out to me so I could work with you and come up with some exercises and some drills. I know it's tempting to say, right? I get this every so often. Like, why do I have to use a table? Seems archaic to find a p-value, because I'll tell you right now, there on your first test, there's going to be questions. I'm going to give you a table, and I'm going to say find the p-value, or a bound on it, right? As we saw, you can't, using the table, you can't typically find the exact p-value, but you can usually make a statement like it's between 0.01 and 0.025. And I'm going to ask you to do that on the test. And it sometimes feels a little unfair because, like, why? SAS told me it was less than 0.0001. That's a lot easier than using a table. I'm supposed to be training you to be a real life statistician. I'll tell you right now, no real life statistician is sitting there in their workplace and they're running an analysis and they get some output and they like pull out a table and start like cross-referencing numbers like we're doing here. However, I will tell you this. Any good statistician in the workplace could pull out a table and answer that question. And the ability, the fact that they could pull that table out and do that is part of what makes them a good statistician, right? That is, there are dots that I want connected. And if you cannot do this, that is a gap in your understanding of what is happening. And it's an egregious gap that needs to be addressed. And I'm going to force you to address it by putting questions like it on an exam. We can hand wave a lot of the math, but there are parts of the math that are so fundamental that we need to understand them. And being able to understand and appreciate the equivalence of, right, these curves and what's underneath them and how these areas of the curves tie into the p-values, that is important. And there's going to be times, that's part of what makes being a statistician so great, is a lot of times as a statistician, you're going to get some question that's just, it's similar to what you saw before, it's similar to what you've done before, but it's also different. And that's cool. It keeps the job from getting boring, but it means that you're going to need to really understand the fundamentals to be able to like make decisions like, am I justified doing this? Or do I need to adjust what I've typically done in some way? And if you don't understand like where these p-values are coming from, then you're not going to be able to answer questions like that. So I am going to hold you accountable to using tables. It's tedious. And I will say this, if you survive the first test, then you are an advanced Stat 512 student, and I will not make you use tables for any class thereafter. Because you'll have proven yourself to me and you'll have earned it. But we're not there yet. And so I'm telling you right now, there's going to be questions, a lot of questions, on your midterm asking you to use tables in various ways. And if you can't do it, you're going to lose a lot of points, because I am a big believer that to really understand how statistics is working, you need to understand where these p-values are coming from. Right? That's what separates you as a statistician from someone who's just like a researcher. Right? I mean, a researcher could like run a software program and look at the p-value column and say it's more or less than 0.05, right? You don't need a master's degree in statistics to do that. Right? What a master's degree in statistics, how that differentiates you from maybe a non-statistical researcher, is that you can do things like this and you understand where these p-values come from, and that's going to give you a great deal of versatility. All right? We could also write SAS code to do it, and I also expect you to understand like how the SAS code's working. So this will actually generate, I think, the exact p-value. I mean, it definitely should. SAS may or may not round the answer. I actually don't think it does, but I kind of foolishly, I don't think I actually put the output there. I mean, you could run this code yourself, of course, very easily. So, right, this is one of the things I think is awkward about SAS, unlike R. R, you could just write like that, where it says answer, you could just write that into a command line in R and it's going to spit out the answer. In SAS, you got to like embed it in a data set and then use like proc print to like see the answer. But basically, what are we doing? The prob t function is what's called the cumulative distribution function for a t distribution. The probability for a t distribution, right? All t distributions have degrees of freedom, so the function needs to know the degrees of freedom. That's the 97. You also have to plug in some number. So whatever number you plug in the first input, it's what that function, the prob t function, is going to do is it's going to say the area to the left of it. So just prob t by itself is saying what's the probability a t distribution is less than 28. But for our p-value, we actually want the probability a t distribution is more than 28. And so that's why we do the 1 minus. Right? Doing 1 minus gives us the probability of being more than 28. And because it's a two-sided test, right, it's not equal to 0 rather than greater than 0. Because it's two-sided, we take that right-hand tail area and we multiply it by 2. Right? And that's exactly how we get that p-value. And then I already showed you in the output that we have the p-value of less than 0.0001. I guess here it is again. So incidentally, I guess while I have the output in front of us, I'm going to talk, I think, in the next couple slides about doing a hypothesis test for the y-intercept. It's very, very similar, right? It's going to be beta naught hat minus 0 divided by the standard error, right? So if I look at that intercept line, if I do negative 243 divided by 15.6, put that in a calculator, you're going to get negative 15.58. If you look at the area, right, in this case, I guess, to the left of negative 15.58, and you double that, that's going to give you the p-value. In this case, that's sort of astronomically, almost immeasurably small. And so SAS says, right, it's so immeasurably small, the best I can do is tell you it's less than 0.0001. All right. Oh, silly me! I forgot step 4. For our slope. Whoops! I messed up our ballroom dance. I apologize for stepping on your feet. So back to our slope. Right, we got our p-value less than 0.001. That's step 3. Right, the most important step is step 4, which is make a decision. So again, I said this: p-value less than alpha. Usually we use an alpha of 0.05. P-value less than alpha, we reject the null hypothesis, right? So again, in this class, it is never acceptable, when I say make a decision, it is never acceptable to just write reject or fail to reject. I always want you to describe what that conclusion means in the context of the problem. What does it mean when you say reject the null hypothesis? And in this example, we would say at the 0.05 significance level, there is sufficient evidence to conclude that the slope differs from 0. That, of course, implies that there's a significant linear relationship between the net girth of a bear and its weight. Right? That would be the type of answer I'm looking for. All right. It's our first 512 hypothesis test. And parts of it are new. Obviously, I mean, I'm not expecting you to have ever done a hypothesis test of slope, but I am expecting that you've done some type of hypothesis testing. And it's the same process as in your basic stats class. Set up your hypotheses, get a test statistic, make a p-value, make a decision. Ha! Here we are. Here's the y-intercept. Now, right, same idea. The typical test, this is at least what SAS is testing in its line, in that intercept line, is that beta naught, the true y-intercept is 0 versus the alternative that it's not. There's the test statistic, just like I said before. Also, right, we could prove mathematically that this thing also follows a t-distribution, also has n-2 degrees of freedom. Now, that said, in practice, this test is generally not one of interest. Right? There are some situations where maybe it becomes useful, especially if we kind of like if we shift or adjust our data in certain ways. But by and large, 99% of the time, and I actually think 100% of the time in this class, a test of whether or not the y-intercept is 0 or not 0 is not important. It's considered good statistical practice in most cases to leave the y-intercept in your model regardless of its significance, We typically only care about the significance of the slope coefficients because those are telling us, right, whether or not those variables belong in our model. So typically it's really only the slope we care about, not the y-intercept. I included the y-intercept here mostly for completeness and also to show, right, that it does have that sort of same general pattern as the test for slope. Yeah, so test statistic is negative 15.58. Mathematically, it's a t statistic, 97 degrees of freedom, and that p-value is very, very small. All right, so that actually kind of wraps up hypothesis testing for slope and y-intercept. I would encourage you to go ahead. This is actually a good time to take a break if you want. This is a natural breaking point in the lecture. It's where I would give you a break in an in-person class. It's where we take a little 10-minute breather. So feel free to pause it, go stretch your legs, do whatever. Maybe go find a loved one and tell them that you love them. That'd be nice. Maybe call your mom and dad. Oh, I bet they'd love to hear from you, right? I'm sure there's something kind of like warm and endearing that you can do with this free time. Put a smile on your face and or someone else's face. And then when you come back, we'll do the second half of the lecture. Okay. All right, welcome back. So what else, right? What else can we get from our proc-reg output? Right, we talked about the significance test, but there's a lot of other stuff there. What else might we be interested in? Well, there's a lot of stuff. Even these extra bullet points are kind of just scratching the surface maybe a little bit more deeply than we have. But still in no way are exhaustive. But they're the two things we're going to talk about as we wrap up this sort of chapter 5 part of the lecture. The first thing that we can get from our proc-reg output that's of use to us is the residuals for each observation. We'll talk about what those are and why they're useful. The other thing is we could get predictions for given values of x, right? We've already seen how to do that by hand, right? But we're going to see how to get SAS to do it for us. And even better, we're going to see how to get SAS to give us confidence intervals or confidence limits for these predictions. All right, so let's start with the residuals. Right, every observation has its own residual, right? So if you have a data set with 99 bears, you have 99 residuals. Each bear has their own residual. The ith residual, right, the residual for some arbitrary bear I in a given data set is defined by, we use the symbol or the letter E hat, capital E hat, to denote the residual, and it's defined to be y minus y hat. Now it turns out that E hat, like the way we're signifying it is very suggestive, right? Because we've been using hats as like best guesses or estimates. Remember, beta 1 hat, for example, is the best guess for the true but unknown slope beta 1. Similarly, E hat turns out to be our best guess for the unknown realization of the true theoretical error E. Maybe that's intuitive. We'll make it a little bit more explicit in the next slide. But before we do that, let me point out, and I think I said this, I think I mentioned this last week, the residuals are essentially, right, when you make the scatter plot and you draw the line of best fit through the scatter plot, remember I talked about how you measure the vertical distance between every point in the line? I said that that's essentially the residual. So that gives us an idea of sort of graphically what a residual is. And this is how we do it sort of algebraically, right? Because remember, again, subtraction is a distance operator. So when I say y minus y hat is essentially, right, the point on the line, or you know, where we are on the line. Y is the actual observation. So y minus y hat is essentially the distance between y and the line. Now here's two formulas from last week, right? We said that y sub I is beta naught plus beta 1 times xi plus ei, right? And then remember that e had all those different assumptions associated with it. Then we had our y hat. So I have two equations, right? If I write y minus y hat and I fill in all those equations and kind of combine terms, what do I have? I have beta naught minus beta naught hat. Now remember, beta naught hat is supposed to be a good guess for beta naught. So that difference should be pretty close to 0. Plus beta 1 minus beta 1 hat, again, that should be close to 0. Times x, but right, something close to 0 times something should also be close to 0, plus the actual error term, right? So we could see that that difference is very close to the error. In fact, if beta naught hat and beta 1 hat estimated beta naught and beta 1 perfectly, then the residual would be the true error. But in reality, they're typically not exactly the same. They're just close. And so instead, what we get is something close to the true error. How close it is, we can see, depends upon how close our y-intercept and slope estimates are to the true values. Now, the ith residual, as I said a couple slides ago, is the vertical distance between the ith observation and the regression line. The sum of these squared residuals, right? So we have the residuals, we square those residuals, we add it all up. That's referred to as the SSE, right? SSE, sum of squared error, right? Because the residual is like an error. In fact, we even called it like an E hat. And there I wrote it out symbolically, right? I have y minus y hat, that's the residual, but I square it, that's the squared residual, and then I have the summation symbol. Now recall, right? Recall from last week that the least squares criterion, the thing that sort of defined what we call or determine to be the line of best fit, is minimizing that particular quantity, right? We said the line of best fit is the one that makes that SSE as small as possible. So the regression line that we're using is the one, right, has the slope and the intercept that makes this particular summation, this SSE, smaller than any other line could do. So what do we do with our residuals, right? Why do we care about them? Well, they could be used in a number of different ways. One, they could be used to test whether or not our linear regression assumptions are satisfied. We're going to discuss this formally and in great depth. We're going to have a fun 4-hour discussion about this in the later half of the class. But it should be a little bit intuitive to us right now, right? Because remember, the assumptions from last week, those 4 assumptions, were all assumptions about the error E. And we just observed that E hat is like our best guess for E. Right? So if I want to test something about the true errors, they're unobservable. So instead I have to look at the residuals, they're like my estimated errors, and work with them, right? Those estimated errors, those residuals, are the only way for me to get insight into the actual errors, E, and of course all the assumptions are assumptions about those actual errors. So we'll see that the residuals play a huge role in testing whether or not those assumptions are satisfied. We could also use residuals to look for or find noteworthy observations, right? Unusual observations, outliers, things like that. Again, this is something we're going to have to kind of defer a formal discussion of, right? But I mean, it's hopefully something that might make sense to us, right? If something has an extremely large residual, right, large in absolute value, that means that it's far from the line. That means that that observation is a lot different than what our model expected it to be. Which could be a red flag, right? It could be something we want to say, okay, here's something that's unusual. I thought it was going to be this number. Instead, it was like 3 times this number, which I observed by this large residual. Let me look at this observation more closely and see what's going on, right? Maybe it's indicative of fraud, right? Maybe it's an IRS audit, and right, this is how we're catching like a fraudulent account. Right? Maybe it's somebody who has some kind of comorbidity, right? Maybe this is like an asthma study, and it turns out this person has some sort of a lung disease on top of it. And that's why we're seeing this large residual. Right? How we sort of use that is going to really vary depending on the context of the problem. We can also use the mean of their absolute value to describe the quality of our model to non-statisticians. It's a very intuitive way to describe how well our model works. In fact, like this idea, the mean of the absolute values even has its own abbreviation. It's called MAE a lot, right? M-A-E, the mean of the absolute errors. It's used a lot in business settings. So like I teach a time series elective. Time series is a type of statistics used a lot in business and finance. And in time series, we talk about MAE, M-A-E, mean absolute error, quite a bit to describe the quality of a model. Right, because the absolute value just tells you like essentially how far you were. It gets rid of the plus or minus. It says, well, for this observation, I was 2 away from the correct answer. From this observation, I was 1 away. This observation, I was 5 away. On average, right, that's the mean. On average, I was within 2 of the correct answer. We could sometimes, instead of looking at the actual difference, we could look at the percent difference. We could say I was off by 1% here, I was off by 3% there, and then you can do something that's called the MAPE, mean average percent error. That's also often used a lot in like business type settings. So you could say, well, on average, my model was within 5% of the true answer, right? My model predicted this. What actually happened was that I was within 5% of the correct answer. I averaged that over everything, and on average, I was maybe 6% away from the true answer. So again, it's a very, very nice way. I think it's something that non-statisticians can understand, maybe more so than some of the other technical terms that we as statisticians tend to use amongst ourselves. And then fourth is we could use the residuals to come up with an estimate of our hypothesized homogeneous variance, right? That's the assumption 2. Remember, assumption 2 is we assume that all the errors had a common variance sigma squared. We can actually use the residuals to come up with an estimate of that homogeneous variance. No, and in fact, here it is, right? So, right, recall from last class, we said our assumptions essentially all 4 could be summarized with the statement that the errors, the actual E's, are IID, independent, identically distributed. They come from a normal distribution with a mean of 0 and a common variance sigma squared that doesn't depend on I and hence doesn't depend on the X's. Again, we can come up with an estimate of sigma squared by using something called MSE. So I'm calling this MSE. MSE stands for mean squared error. It's denoted by sigma squared with a hat over it. Again, the hat's denoting that it's a best guess. It's an estimator of the true but unknown sigma squared. And so we have this MSE. The MSE, what is it? The numerator of that fraction is just the SSE, right? So the MSE is the SSE divided by n minus 2. And that does look a lot, it looks a lot just like the variance formula from like a chapter 2 in a beginning statistics class, right? You have like a sample variance and like a sample standard deviation, and we call them S and S squared. This formula does look a lot like that, doesn't it? What's the formula for S squared? The formula for S squared is x minus x bar squared over n minus 1. Oh, sorry, the sum of x minus x bar squared over n minus 1. This looks a lot like it, right? It's x minus the best guess for x. Here it's y minus the best guess for y. We square that, we sum it up, right? It's a little different because we're dividing by n minus 1 instead of n minus 2, but we already kind of talked about why n minus 2. N minus 2 because, right, we're estimating two parameters. We're estimating a y-intercept and we're estimating a slope. And so, right, just like S squared estimates a population variance, so too does this MSE formula estimate a variance as well. All right, so that's our discussion of residuals, some things to think about. Hopefully most of it made sense, big picture, although as I implied, some of it we're going to talk about down the road once we've kind of built up some other terms and concepts and so forth. The last thing that I want us to talk about before we wrap up chapter 5 is predictions. So remember we said last week that generating a prediction for y for a given value of x was as easy as just plugging the value of x into that least squares regression equation. And we've done a few examples already where we do it by hand. We're going to see how to do it with SAS. But before we do that, I want to talk about two important concepts, and that is interpolation and extrapolation. Okay? Interpolation is predicting y for values of x that are within our observed x values. Extrapolation is predicting y for x values that are beyond our observed x values, right? So imagine that, right, our neck girth, imagine that we have a sample of 99 bears, and for those 99 bears, all their neck girths are, say, between 5 and 10. Then if we generate a prediction for an x value between 5 and 10, that's an interpolation. It's inside the observed range of values. If we generate a prediction for a neck girth smaller than 5 or more than 10, that would be an extrapolation, right? We're predicting for values of x's outside of our observed x values. Which of these two do you think is the more dangerous one? Do you think interpolation is more dangerous? Or do you think extrapolation is more dangerous? Or, I don't know. Danger is cool. It makes us sound like we're like we're really living life on the edge. Maybe which one do you think is the least reliable or less precise? Exactly, right? Extrapolation, right? Because we're making predictions for values of x that just aren't in our data set, right? So we're kind of saying a guess, right? Interpolation is we build a model. That model essentially is built on, say, right, x's from 5 to 10. And anytime we predict beyond 5 or beyond 10, we're sort of assuming that the linear pattern we've observed between 5 and 10 extends beyond those numbers. But of course, that's an assumption, right? And that assumption may or may not be true. Usually extrapolating a little bit is not a big deal, right? Maybe doing a prediction for 4, maybe doing a prediction for 11 is not bad. But the farther we move away from our observed x values, the sort of riskier it ends up being. here's an example. This is actually a really cool example. This is actually, it's, yeah, true story. Autobiographical example. Kind of a fun use. Like, I don't know. It's good to talk about like how statistics can make us happy. It could make us rich. It could get us a fantastic job that's really interesting. Gives us the kind of job that just everyone envies. But statistics can be used for more than that. It could actually be used to improve our love life, right? So like imagine that oh man, you're dating, right? And you're in a relationship and it's going really well and you're like, man, like I know this is the one. And you kind of reach that pivotal moment in a blossoming relationship where your boyfriend girlfriend says, "Oh man, I want you to come meet my parents." Oh man, whew, yeah, that's a tough time, right? It's nerve-wracking because like you're with the person that you love, you want to make a good strong first impression. And so what would you do? You're like, well, maybe I'll buy a present, right? I'll bribe them. Maybe I'll buy like a really nice sweater for my significant other's father, right? Oh, that's nice. So the problem is what? The problem is sweaters come in sizes. You walk in the sweater store and there's like small and medium and large and extra large, and I don't know. It would definitely be awkward to buy the wrong size, wouldn't it? Man, I guess I guess if you're tacky, if you're insensitive, you might like ask someone, "Hey, how big's your dad?" But I don't know that you're allowed to ask those kind of questions, right? So what do we do? Well, this is what I did. This is what I did with with the wife that I currently have. Worked for me. Is you say, hey, I can't ask how big your dad is, but why don't you tell me how old he is? It's okay to ask that. And I asked her. She said, oh yeah, my dad's 50 years old. I said, okay, perfect. I know that there's a strong linear relationship between how old someone is and how tall they are, right? Just ask any elementary school teacher. The problem was I had to quantify this. So, right, what I did is I went down to the local elementary school. Around about recess time, I took a sample of 30 small children, right? I asked them their age. I measured their height. I may or may not have gone to jail for a short period of time, but afterwards, right, I took this number, this information, I put it in SAS, I crunched the numbers. Oh, what a foolproof plan, right? Statistical love. And I found my regression line. The y-intercept was 10. The slope was 4. All I have to do is just plug it in. So I think next slide. All right, let's see how big my future father-in-law is gonna be. I know he's 50 years old, so 4 times 50 plus 10. Oh my. 200, this is why I'm like 210, that seems like a lot. But then I realized that my units were inches, right? Never forget your units. So I'm like, all right, 210 inches probably isn't that big. You just divide it by 12 and, well, still kind of large, I guess. Oh, man. Seemed like such a good idea in the moment. 17 and a half feet tall. 17 and a half feet tall. You definitely don't want to mess with that father-in-law. Ah, man, where did we go wrong? I mean, I definitely don't shop there, but I have seen big and tall stores in the mall. They do exist. It might be a really big, really tall store. Yeah. Yeah, I know. I mean, it's a silly example, but it does showcase, right? I mean, where did we go wrong? We went wrong because we wildly extrapolated, didn't we? our data was only for ages 3 to 10, right? Our observed X ranges were 3 to 10. Trying to predict the height for a child between ages 3 and 10, this equation would probably work pretty well. And to be honest, maybe it would work well for a 2-year-old or an 11-year-old. But what happens, right? Sure, children are growing, but at some point we hit adolescence and that growth stops. Right? That upward sloping line flattens out. At some point, maybe even starts to decrease as our bones settle. But of course, anytime we're using the prediction equation, it's assuming that that linear upward trend is going on. In actuality, probably no example is it going to grow forever, right? Nothing grows forever. At some point, it has to either flatten or reverse trend, and that's certainly the case with a human's height, right? But because my extrapolation assumed that every year a person continued to grow 4 inches, even through their 20s, even through their 30s, even through their 40s, it assumed that my future father-in-law was 17.5 feet tall. And then let me tell you, it definitely made for an awkward first Christmas. All right? So we want to be careful when we generate predictions, right? Particularly anytime we extrapolate. Now, the last thing for us to discuss with respect to predictions is the last missing piece. And that is we generate a prediction, maybe a ridiculous one like 210 inches. But how do we add to that a proper quantification of uncertainty? For example, let's go back to our bear data set, right? Because the sweater example is just a little bit too personal and just a little bit too embarrassing. Based on our data set, we would expect a bear with a neck girth of 20 inches to weigh 167.45 pounds. You should be able to go back to the output from the previous slides and verify that yourself. If you can't, you should reach out to me. However, do we expect him or her to weigh exactly 167.45 pounds? Of course not. Really, what we're saying is we probably expect them to say, well, my best guess is that they'll weigh 167.45. In actuality, they'll probably be somewhat close to there. And of course, someone might come back at us and say, okay, how close do you expect? And now we need to find a way to quantify that closeness, right? The idea of quantifying closeness is most often answered through confidence intervals. Yeah, we did it all today, didn't we? We did a little bit of hypothesis testing, and now we're going to wrap things up with some confidence intervals. Now, when we're talking about these prediction equations and their associated confidence intervals, there's actually 2 types of confidence intervals. For a given value of x, we can find 2 things. We could find a confidence interval for the mean value of y for all individuals with a given value of x. This is called a confidence band or a confidence interval for the mean. We could also find a confidence interval for the actual value of y for a single individual with a given value of x. This is called a prediction band or sometimes called a prediction interval. So question to you, for a given value of x, which of these do you think is going to be bigger? Right, a bigger interval sort of implying more uncertainty. Exactly. The second one is always bigger, math fact, than the first one. It's a little bit kind of like the central limit theorem, right? Central limit theorem from our basic statistics class, right? Central limit theorem basically says what? It says that the variance of x bar is less than the variance of x, right? The variance of a sample mean is less than the variance of a single observation, right? Central limit theorem says variance of x bar is sigma squared over n. The larger the sample, the smaller that variance gets. It's the same idea here. There's more uncertainty in a single observation, right, a prediction, than in the aggregate, right, when we're looking at the mean of a large group of people. And so because of that, a prediction interval will always be larger than a confidence interval for the mean. If you're a formula kind of person, you can actually look at these formulas. They're a little bit ugly looking from our textbooks. I'm gonna focus not so much on the formulas. I'm gonna focus on a couple like big picture like takeaways from them, and then of course show us how to use SAS to calculate them for us. So I kind of like things like this when I look at a formula, right? I say, okay, looking at this formula, like what happens the further x gets from x bar, right? X bar is like that sample mean. You can think of it as kind of being like right smack in the middle of like those observed values of x, right? So if we're predicting if our observed values of x are between like 5 and 10, then our sample mean, you know, might be somewhere in that 7.5 range. So as we try to generate predictions further and further and further from 7.5, what do you think's happening to our intervals in either case? Exactly, right? The intervals are growing. Right? The further we get from x bar, right, the further we get from kind of like where our information is most concentrated, well, we have sort of less information the further out you go, which kind of means that there's more uncertainty. We want to reflect that uncertainty, and when we do so through a larger interval. Again, if you look at the formulas in the textbook, you should be able to see algebraically how that happens. The size of the interval also depends on the sample size, right? It should be intuitive that larger samples will give us smaller confidence intervals. Large samples means more information. More information means more certainty, i.e. smaller intervals. It also depends on the MSE. Intuitively, we should expect that larger MSEs will be associated with larger intervals, right? The MSE, right, the mean squared error, is our estimate for that homogeneous sigma squared, the sort of inherent variability in our error. If there's a lot of underlying variability in the error, then that's going to reflect itself in sort of more error in our confidence intervals. It's going to propagate. And we're going to have larger confidence intervals because of it. Right, so all three of those answers should be intuitive, and you can also sort of confirm them algebraically by looking at the formulas in the textbook. All right, how do we get this in SAS? We get this in SAS also through proc-reg. At the end of our model statement, we can use a slash, and we can ask for a whole bunch of extra output. There's a ton of things you can put after the slash. Two of those things are CLI, which will give us the prediction intervals. That CLI stands for the confidence limit of an individual. And CLM stands for the confidence limit of a mean. All right, and this is what it looks like, right? So it's just a portion of our output. Shows us bears 1 through 41. It shows us what the actual y was, right? So bear number 1 had an actual weight of 65. Our model predicted that that bear's weight would be 64.8. The residual, y minus y hat, is all the way over on the right, and we can see it, that's 0.2. There's a standard error of the mean prediction. Don't worry about that for our class. That's just it's part of the formula that's used to calculate the confidence intervals that come afterwards, right? So we can see the confidence interval for the mean is at 53 to 76, and the confidence interval for an individual, the prediction interval, is that -9 to 138. Is that easy enough? Does that make sense? Oh, excuse me. Let me yawn. Yeah, so as expected, right? As expected, that prediction interval is larger than the confidence interval for the mean. Now, one piece of information that I think is sort of awkwardly absent is the x variable, right? Because, for instance, you look at that predicted value, that's 64.8. Like, how would we interpret that? It's basically like we would predict a bear with an x value of whatever bear one has to be 64.8, but we don't know what that is. It's not outputted for us, at least in this part of the output. Now, of course, we know we could just use like proc print and find it that way. But it does, feel tedious to have to kind of like do that extra step, because the interpretation of a lot of things, particularly the confidence intervals, how we interpret them depends on the x. I went ahead and did proc print for that first observation and found out that the neck girth for that bear was 15. Right? So the predicted value was what we would predict the weight to be for a bear who has a neck girth of 15. And then, right, to me, my favorite part of the bear data set is that the bears have names. And so that bear's name is Alan. So, first let's start with this. The confidence interval associated with bear number 1. This is the confidence interval for the mean. That confidence interval was 53 to 76. We would interpret it as this. We are 95% confident that the true mean weight for all bears with a neck girth of 15 inches is somewhere between 53.39 and 76.2, right? If you look at a slice of bears, just the bears that have a neck girth of 15 inches, right? Some of them weigh more than expected, some of them weigh less than expected. What is the average weight for all of these bears? Well, we don't know it exactly, but we're 95% confident it's somewhere between 53 and 76. The second type of interval, the prediction interval, was the much larger one, and that is what we would predict the weight of an actual individual bear is, right? If somebody said, hey, like your best friend called and said, you'll never believe it, I just bought myself a pet bear. And they say, that's pretty cool. What's its neck girth? And your friend says, your buddy says, oh, its neck girth is 15 inches. And you say, well, let me guess what I think that particular bear weighs. Right? In this case, we don't have a lot of certainty in our guess. We think there's a 95% chance, we're 95% confident that it's between -9 and 139. Pretty broad range of values, perhaps so broad that it's not particularly useful. The size of that interval, right, is being contributed to by perhaps a relatively small sample size, the fact that we're predicting away from X bar, and of course just the inherent variability in a bear's weight, right? That essentially that MSE. Okay. So hopefully we understand the distinction between those. Again, if not, you can reach out to me. There is, of course, right? I should be saying, you should be supplementing these lectures by reading the textbook. That's always important, but I think it's even more important when you're learning online. In a classroom, I could draw a lot more pictures more easily. I can read the classroom and see what's clicking and what's not clicking. I can throw up some extra equations quite quickly. That is, there's a lot of versatility to sort of being in a live classroom that we're sort of missing out on here. Pictures really in particular. I can't make the same kind of high quality graphs that a textbook manufacturer can afford to do. I do my best, but I do think that the textbook really does sort of supplement kind of what we're talking about, particularly kind of on a graphical level. So I would strongly encourage you to be reading the textbook as well to supplement what we're talking about. That, of course, will give you hopefully further reinforce the distinction between a confidence interval for the mean and a prediction interval. But if not, right, then reach out to me. I'm waiting to hear from you. Callers, professors are standing by. We can look at these confidence intervals. We can actually generate a graph of the confidence intervals or the bands with proc Gplot. And this is what it looks like. They're always kind of at their narrowest in the middle, right? Because we know the bands are smallest, the confidence intervals are smallest around X bar. In this case, actually looks like X bar might be somewhere around 20. And then particularly if you look at that shaded blue, the shaded blue is the confidence interval for the mean. That looks relatively small, right? And you can kind of see as you're moving away from the mean, it is kind of widening a little bit. That effect is also true in the prediction interval, but it's subtle enough that it's hard to see with your eyes. But it is happening, I assure you. We could also see in this case the prediction interval is actually quite a bit larger than the confidence interval for the mean, isn't it? I don't know that we got an appreciation of how much bigger it is just by looking at the numbers. So again, like having this picture is kind of nice, I think. Now, there is a little bit of a downside about the methods that we've used, right? The methods that we've shown, we can only create exact numerical confidence intervals or prediction intervals for certain values of X. What are the ones that we can generate? Exactly, right? SAS is only generating confidence intervals for values of X that are inside our observed data set. Right? If for some reason there was not a bear in our data set who had a neck girth of 18, then we don't know what the relevant confidence intervals are for a neck girth of 18. For the prediction itself, that's not that big a deal. We can generate the equation, we could plug 18 in, we could get a prediction, but the formulas for the prediction intervals are cumbersome enough that we would not want to do those by hand. So what do? Well, the process works like this. You add an extra observation, right? So we had 99 observations. We're going to add a 100th observation. The 100th observation has the value of X that we're interested in. So say the 18. For that 100th observation, we set Y missing. Because Y is missing, SAS cannot use this observation in terms of constructing the regression line. So it doesn't change the regression line, but it will use the X value when generating the confidence limits from the CLI CLM statement. Pretty cool, right? Now you should know how to do this based on Stat 511. So I am not going to make it explicit for you, at least not right now. I want you in your upcoming lab to think on your own how you would actually go about and implement this process, right? The more you do it yourself, the more you grow. The more I do it for you, the less so. All right. That wraps up chapter 5. So all that we have remaining is chapter 6. And chapter 6 is it's a short chapter, and we've actually already covered a lot of it, right? I don't know. To me, I don't know. You may or may not agree with me. I think you will. I mean, I've taught this enough that I feel like I know what resonates with the students, at least for my teaching style. Our book kind of weirdly teaches regression and then correlation, right? I taught sort of the opposite. To me, it feels more intuitive to start with correlation, and then correlation just sort of naturally leads us to a discussion of linear regression. So, right, our book kind of does regression then correlation. I taught correlation then regression. So, right, we actually already know a lot about correlation. But there are a couple parts that I kind of want to kind of expand upon. All right, so let's kind of look at those things. So recall, right, from not that long ago, that R is our sample correlation coefficient. I did not tell us that this is a statistic. I mean, we should have known that. It's based off a sample. Anything based off a sample is a statistic. And it's used as a best guess for, that's the Greek letter rho, the population correlation. As such, we can use R as the foundation of the following hypothesis test. We could test whether or not there's correlation. Is the correlation zero, i.e. X and Y are uncorrelated, or is the correlation something other than zero, i.e., right, they are correlated with each other. Here is our output from ProcCore. We see the correlation, that's the 0.94543. If we look beneath it, we see a less than 0.0001. That's the p-value for the hypothesis test of whether or not rho is zero. In fact, we can see it, right? SAS always tells us, if you read right above that grid, right, there's sort of two lines. Do you see it? The first line says Pearson correlation coefficients, n equals 99. And right beneath it, it says prob greater than absolute value of R under the null hypothesis that rho equals zero. It's basically saying the top number is the correlation, the bottom number is the p-value. Right? Because it can sometimes be easy to confuse them because, right, p-values are decimals and correlations are decimals. So, right, sometimes you can confuse them if you're not careful. Top number is correlation, bottom number is the p-value testing whether or not that correlation is significantly different than zero. Now, less than 0.0001 should inspire a certain amount of deja vu. We've seen that number before. That is, in fact, the p-value for the significance test of slope. Well, because it's a bound, it's hard to appreciate the fact that I'm going to state. But if we were able to estimate the p-value for slope more accurately or more specifically, we would observe that the p-value for testing the correlation is actually the exact same as that of testing the slope. And that should be intuitive because they're doing the same thing, right? Whether or not correlation is equal to zero, it turns out is equivalent to testing whether or not the slope is equal to zero. And that means that any test will always have the same conclusion, and we get that same conclusion because the tests will always have the same p-values. Yeah, so just like before, it's the exact same. That SAS does not report the test statistic, but the test statistic it used to get that p-value is the same test statistic, right? That 28.58. It follows a t-distribution with n minus 2 degrees of freedom. And as I said, the test statistic, degrees of freedom, and p-value for testing the significance of slope equal to 0 will always be exactly the same as testing the significance of correlation being equal to 0. All right. One last thing, and that's this thing called coefficient of determination. This is going to be what we end this lecture with, in this week with. It's going to be where we pick things up next week. It's going to be our bridge, our springboard. The coefficient of determination is referred to as R squared. It's the percent of the variability in y that could be explained by its straight line relationship with x. It feels a little magical, right? Because the R I'm talking about is the correlation. So I'm basically saying if you square the correlation, well, correlation is between -1 and 1. So certainly we know if you square it, you're going to get something now between 0 and 1. So all right, I mean, we should be able to see that. What's maybe not obvious is that this turns out to be the percent of the variability in y explained by, so the technical term is its straight line relationship with x, although we often just say the percent of the variability in y explained by x. A little less of a mouthful. It might seem a little out of the blue that it works that way. We will show why. I'll demonstrate why this is next week in a little bit more depth. Only so much we can do in 1 week. And then kind of as I already stated, unlike R squared is always non-negative. It represents a percentage. Makes sense, it's just between 0 and 1, and we know what that percentage is. So here's an example. Say that we find right, that the correlation between x, the time a Stat 512 student studies for their first exam, and y, the score they get on that exam, is found to be 0.70, right? Strong-ish, positive linear relationship. The R squared would be 0.7 squared, right? 0.7 squared, put that in your calculator, you get 0.49. That means that 49% of the variability in exam scores is explained by its straight line relationship with how much time was spent studying, right? 49% of the variability in exam scores is explained by the amount of time spent studying. Okay? Does that make sense? Like what am I saying here? I'm saying that in, I don't know, I guess a month-ish maybe, you're all going to take your first exam. And I'm going to grade that exam. And what am I going to observe? I'm going to observe that different students get different scores, i.e., there is variability in your test scores. That's nothing profound, right? If everyone in the class got the exact same test score, I would accuse you all of cheating and try to get you all kicked out of Westchester, right? Try to get all of you sent to Narnia or Jersey. Right? We expect there to be variability, right? All we're saying is that it would be weird if everyone got the same score. So the question that a statistician asks, right? The core of being a statistician is why? Why is it that different students get different scores? It's a good question. It's a tough one to answer. It turns out part of the reason that different students get different scores is because different students spent a different amount of time studying, right? Some of you studied night and day. hundreds of hours. Some of you, right, maybe only studied 1 or 2 hours. Right? Not judging, right? Maybe some of us work more than others. Maybe some of us have kids, some of us don't. I mean, for whatever reason, right? Some of us study more, some of us study less. We all do our best. It turns out that this one factor, right, the fact that students spend a different amount studying, actually explains a substantial amount of the variability, right? Essentially half of the variability that we're observing. It's a lot, but not all of it, right? That is, right, if the whole class made a pact and the whole class said, all right, we're all going to study exactly 20 hours, no more, no less, right? We take that sort of factor out of the equation. I would still expect to see variability in test scores, agreed? That is, even if you all studied the exact same amount of time, I would still be surprised. I would still ship you all to Siberia if you all got the exact same test score. So that is, there's some remaining leftover variability. That's the remaining 51%, right? Why? Why is there still variability? I certainly would expect there to be less variability, right? If we all studied the exact same amount, I bet like our test scores would all be kind of closer to one another. There would be less variability, but there would still be some variability. Why? Well, because the amount of time that you spend studying is not the whole picture, right? There's these lurking variables. There are these other variables at play that also make a difference, right? It's not just how much time you spend studying, it's maybe the quality of time that you spend studying. Maybe some of you are watching TV, maybe some of you aren't. It's whether or not you've taken that introductory statistics class. Some of you have, some of you haven't. If you have, probably life's a little bit easier for you. Right? It's whether or not you got a good night's sleep. Some of you did, some of you didn't. It's whether or not you remember to put batteries in your calculator. Most of you will, maybe one of you won't. Right? There's all these other factors, right? All these other X's. And they are the ones that are driving that remaining 51%, right? So it turns out one variable accounts for like half of it. That is a lot, but not surprisingly, there's something left over. And what does that motivate for us as we get ready to transition into next week? It motivates the idea that like simple linear regression's pretty cool, but it cannot answer, right, the whole picture. Simple linear regression, in this case, gets 49%, but there's still 51% left over. And to be able to tackle that 51%, we're going to need to somehow be able to account for these other factors or these other variables. And that's what we're going to learn to do next week. All right. In the immortal words of my favorite philosopher, Coyote Peterson, oh, by the way, a big bear enthusiast. Be brave, stay wild.